morning session. I'm going to start with linear minimum variance estimation. But please recall what we have done and how we got here. We first introduced the concept of least square estimation, given observations alone. Nothing else was given. Z is equal to h of x. H is known, Z is known, I want to estimate x. There we split the problem into two parts. One, m is less than n, and m is greater than n. We did this largely to be able to introduce two things. That least square problems are different from solving a square system, a linear system. X is equal to b where A is a square matrix. So when the matrix of the linear system is not a square, you can have a long matrix, in which case m is greater than n. I can have a broad matrix where m is less than n. With me? So we essentially talked about methods for solving linear matrix systems when the matrix either long or broad. In the case of a long matrix, we found out that there may not in general exist a solution. In the broad matrix, there are infinitely many solutions. We wanted to be able to get the best estimate of x. In one hand, for the long matrix, we converted that into an unconstrained minimization. In the broad matrix, we converted it into a constraint minimization. Along that process, we also learned two different techniques, one for unconstrained, another for constrained, Lagrangian multiplier. That was the outcome. Data assimilation is intimately associated with optimization. So I wanted to present the variety of optimization problems that can arise while doing the estimation problem. Are you with me? So we killed multiple birds in one stroke. That's a saying. I'm a vegetarian, please. I don't shoot anything. It's a manner of saying. Are you with me? Okay. Once we did that, we wanted to come into what's called 3D war. 3D war is closely associated with Bayesian formulation. Before you game into the game, you have a prior. During the game, you learn new information. At the end of the game, you are not the same person that you entered the game before it started. You have learned new things. So your new state has to be characterized. This characterization can be done in one of two ways. Either you work in the state space using least squares where you talk about the estimates of the state, or you can work in the probability space. You have an input distribution, which is the prior. We have a conditional distribution during the game, and the game transforms the prior into a posterior, so you can work in the space of probability distributions. These are two competing approaches. But once you get the posterior, you cannot tell that I got a posterior distribution. You have to generate a forecast. The forecast is a state. So how do you get a state from the posterior? One is mean of the posterior. Another is the mode of the posterior. Another is the median of the posterior. All of it, please? Ultimately, the aim in prediction is, to the common world, they don't care about probability distribution. Tell me there's going to be a 5 inch of 50 millimeter rain or 5 millimeter rain. That's all they care for. 5 millimeter or 50 millimeter, they are the state information. So how do you convert your probability information into your state information? I can compute various types of statistics from the posterior mean, the posterior mode, the posterior median. You all should know the mean and the median coincide when it is unimodal, Gaussian distribution. So here comes the question. If the prior belongs to one class, and if the conditional distribution belongs to another class, what will be the class of distribution the posterior would be? Dr. Vineet gave a good introduction to that. If the prior is Gaussian, and if the conditional distribution is Gaussian, the posterior will be Gaussian. This property within the Bayesian philosophy is called reproducibility of distributions. The Gaussian distribution prior reproduces itself as a posterior distribution if the conditional distribution is also Gaussian. So Gaussian, they are called conjugate distributions of each other. So there is a general theory of conjugate pairs within the framework of Bayesian theory. If the prior belongs to class A and the conditional belongs to class B, then the posterior will belong to the class A. I want to be able to reproduce class A distribution. I want to remain well within the class A distribution. What kind of conditional distribution will enable you to induce this reproducibility property? That's one of the grandest theorems within the Bayesian circle. Are you with me? I want you to understand there are multiple ways of looking at this. Then we introduced 3D VAR. 3D VAR, we did not work in the space of distribution, we worked in the space of states. I have a prior. The prior has some uncertainty associated with it. The prior has a covariance. Observation has a distribution. Then I combined the information in the prior and in the observation, and we found an estimate which lies on the line joining the prior and the new information. That's 3D VAR. Yesterday, then, we did the 4D VAR. All of you? 4D VAR is a separate philosophy where the dynamics comes into play. In 4D VAR, because of shortness of the time, we only considered the problem of estimating the unknown initial condition. More often than not, the parameters of the model may be unknown too. We can use the same framework to be able to estimate the parameters and the initial condition in 4D VAR. So what's the ultimate aim? Again, I have to reduce the problem to one of optimization. The crux is in computing the gradient. Computing the gradient of the objective function in the dynamic context is not a trivial task. You simply cannot differentiate. We did, but that involves heavy lifting in computation, matrix multiplication. We wanted to avoid that. A clever means of avoiding excessive computational demand is to rewrite it as a backward adjoint equation. So by running the model forward, running the adjoint backward, both are of similar complexity. By one cycle, I computed the gradient. Then I updated the initial condition. Repeat the cycle, repeat the cycle, repeat the cycle. How long? I need to have an exit condition. The exit condition is always based on the magnitude of the gradient. If the magnitude of the gradient is small, we believe we are somewhere closer to the minimum. And that's conditioned on the assumption that there is a unique minimum. But there could be a lot of troubles. Suppose I have a cost function. The surface of the cost function has a lot of plateau. What is me? So if there is a patch of land, that's a plateau. If I approach this, I will stick here. If I approach this, I will stick here. If I approach this, I will stick there. So to avoid that, what is it you need to do? You need to be able to be very careful in designing your objective function. That could lead to multimodality. In general, for nonlinear case, that could be multimodal. We have given in our book an example of multimodal. I keep talking about the book. You have the entire book in the lecture form in NPTEL 40 lectures. All of you? How many of you have visited NPTEL lecture series? Please do, please do, please do. And the proof of the pudding is in its eating, right? How do you test whether you understood problems? So here is a set of problems I generally use for my class. I give you a 2-semester course. I'm going to give this problem set to Dr. Kutty. He's going to make it available. Are you with me? I was telling my friend this morning, you all have to work at least until you are 65. Do you realize that? And you are all in your 20s. You have 40 years of productive life in front of you. So don't be in a hurry. The road is long. Don't pick up speed now. Go slow. Learn well. If you learn well early, that's going to guide you for the next 4 to 5 decades of your career. And how do you do that? Staying with the problem, working hard, testing your understanding. So I'm going to leave you a present, a set of all problems. I'll be delighted to help you, but you should attempt it first. Don't seek solutions. That's easy cop out. You have to try, you have to crash your head. Please do, he will make it available. Now, why do we do this? I wanted to now tell you that we are going to turn the page. We are going to be looking at another important concept. Yesterday, my friend talked to you, asked me a question about blue. Best linear unbiased estimate. Blue is one of the ways in which Kalman filter can be derived. There are about 6 to 7 different various derivations of Kalman filters. With me? Blue is one of the easy ones. Bayesian is another one. The Bayesian, he did in the probability space. I did it in the state space as the 3D var. Everybody? I want to do the linear minimum variance estimation and then show you the bridge between linear minimum variance estimation and the Bayesian estimation to see that they are one and the same. So you, at the end of this, you'll have at least 2 ways of looking at Kalman. All of you? I'm trying to summarize this because I don't want this to be a loose connection. That should be a very tight connection between all the topics. And it is the more you understand the tightness of the connection, better you are going to be. With me? Good. So let me begin. X is an unknown. I am given 2 pieces of information. X1, X2. X1 and X2 are random. X1 and X2 are random. Expected value of X1 is X. The expected value of X2 is also X. The variance of X1 is sigma 1 square. The variance of X2 is equal to sigma 2 square. So given X1, X2, and the variances, and the fact that both of them have same expectation as the original unknown. Do you see the problem? My job is to be able to arrange an estimator to estimate X based on the 2 information. So first I want you to think about the notion of an estimator. What is an estimator? Estimator is a function of the observation. The estimator is going to be a surrogate for the unknown. All of you? You are going to gain knowledge about the unknown through the estimator. I don't want to repeat this. I'm sure you have heard it a million times. Given a coin that falls head with probability P and the tail with the probability 1 minus P, how do you estimate P? How many of you know answer to this? Think about it. Raise it. I'm going to give you a couple of minutes for you to think about it. Do you know this? Can you do that? Come on, guys. How many of you are confident of doing this? My suggestion is this. Don't worry about Kalman filter until you understand how to estimate the bias of a coin. The twinkle, twinkle, little star of estimation problem. All of you with me? Come on, guys. That's a model problem. Every book in probability statistics would have that. So what are the questions we need to do? I'm going to toss a coin. I'm going to get a sample. I have to concoct a function of these samples. that is going to lead me to an estimate of P. I can't get P, I only can get P hat. So P hat is an estimate of P. And what is that I would like? P is fixed. P hat is random. Why P hat is random? The results of the tosses are random. Any function of a random variable is random. P hat as being an estimator, which is a function of the observation, is random. So you are trying to approximate a deterministic quantity using a random quantity. So you need to consider what's called the sampling distribution of P hat. I hope you all understand that, right? Every random variable must have an inherent distribution. That sampling distribution will have a mean. That sampling distribution will have a variance. How do you estimate the goodness of your estimate P hat? The variance of the sampling distribution must go to 0 as the number of samples becomes larger and larger and larger. Secondly, the mean of the sampling distribution must coincide with P. All of it, me please? The condition that the mean must coincide with the mean, with the unknown, that relates to the notion of bias. If the mean of the sampling distribution is not equal to the unknown, your estimate has a bias. Unbiased means the mean of the sampling distribution coincides with the unknown. Best, I'm talking about blue. U for unbiased, B for best, L for linear, E for estimate. So in the case of coin tossing, what is that you do? I define a random variable. If it is head is 1, it is tail is 0, add all the excess, so that's linear. So in what sense is going to be best? I want to be able to reduce the sampling variance. So you need to be able to compute an expression for the sampling variance. Anybody who has done the job, the initial distribution is a Bernoulli distribution. The variance is PQ. If you have n tosses which are independent, the variance is going to be PQ over n. The variance goes to 0 as n goes to infinity. So in large samples, my estimate P hat will converge to P. All of you with me? How many of you are with me? That's right. I want you to be able to go home and prove it in your notebook and have it done. Because you should see at least one proof of the fact that I have a problem where I can concoct an estimator. I can prove that this estimator asymptotically becomes better and better and better. As the end, the number of samples becomes increasing. Are you with me? That's a good starting point for estimation theory. So I talked about a blue in the context of estimating P, the probability that a coin falls head. Now I'm going to talk about blue in a general context. In the case of a coin tossing, I can toss the coin. I don't have much to spend, so I can generate lots of samples. Here I was given only 2. You have to work with what you are given. You cannot ask more than what you are given. So x1 contains information about x, x2 contains information about x, x1 is random, x2 is random. They expect the distribution of x1 is such that its mean is the unknown, its variance is sigma 1 square, the mean of this is equal to that, the sigma, its variance is sigma 2 square. All of you? That's right. Now, what is an estimate? So let x hat be an estimate. I want the estimate to be linear. What's that means my estimator is a linear function of the observation. So how do you concoct a linear function used on 2 variables? Ax1 plus bx2, linear combination. All of you? So let x hat be a plus ax1 plus bx2. Now I'm going, so I have already satisfied linearity. The L in blue is taken care. Now I'm going to talk about U. In order to force U, what is that I need to do? E of x hat must be equal to x, and that must be equal to A1 times E of x1 plus B times E of x2. So, but this is x1, this is x, this is x. This is A plus B times x. So x must be equal to A plus B times x. That implies A plus B must be equal to 1. So I can force unbiasedness by requiring a coefficient to be sum of the sum of two coefficients is equal to 1. If sum of two coefficients is equal to 1, I can express one in terms of the other. I can set B is equal to 1 minus A. Therefore, my expression for the estimate is AX1 plus 1 minus A times X2. Now let's look at it a little bit geometrically now. You should all know X1 is a point, X2 is a point. Now, X1s could be, all of these can be scalars, all of these could be vectors as well. Are you with me, please? So my treatment cuts across all dimensions of X. X could be a vector, X1 is a vector, X2 is a vector. If it is a vector, I have to deal with covariance, which I could, but to make life simple, I'm essentially dealing with scalars. Please understand, I had to walk before you run. Are you with me? That's right. I'm telling these things, it's not that you don't know, but I want to keep reminding you. Don't be in a hurry. Please remember, you have 40 years of life in front of you. Academic life.
How did the expectation of X cap become X?
What's that? That is the requirement from for unbiasedness. X hats are good question. X hats are unvariable. X hat is an estimate. For that estimate to be unbiased, its expectation must coincide with the unknown. Hey, that's why the coin tossing problem. Why do probability people talk about coin tossing? Because they want to introduce most elegant principle using the simplest problem. Are you with me? That's right. Most elegant principle that is the basis for estimation using the simplest possible case. All of you? Come on, guys. You don't have to have a radar. You don't want to have all this. I want to collect observation. Observation can be collected simply by tossing. What could be better? Are you with me? So observation means don't think of radars. Don't think of satellite all the time. It's a way to conduct experiments. That's key. That's key. Are you all with me? So have I now satisfied U? Have I satisfied L? Have I satisfied E? Is an estimate, is unbiased, is linear. So what is the rest of the story? I got to introduce B. B in what sense? I want the estimate to be such that its variance must be minimum. How many of you have been talking about uncertainty? That's a big word, right? Uncertainty quantification is a big word. Yes, it is. It ought to be. So we have to now worry about the uncertainty in the estimate. You measure the uncertainty estimate by the variance. If the variance is large, it can take values in a larger domain. If the variance is small, its values are set to a smaller domain. Asymptotically, if I can make the variance go to 0, the estimate becomes more and more and more and more reliable, more and more concentrated. In probability theory, there's a term for that. The estimate P hat converges to P in probability. That's a theorem in probability. The probability that P hat of n tends to P, absolute value greater than delta, is less than or equal to 1 minus epsilon. In the as n becomes large. This is the estimate. This is the real value. The difference between them is greater than, sometimes you use the epsilon and delta like this. That's right. The probability that it differs from the true value by a small amount is also small. That's a mathematical expression of telling that probabilistic quantities, how close probability quantities are. In the deterministic way, how do you do that? Norm. The norm of the difference. Are you with me, please? But in this case, this is also a norm. Why? If P is a number, Pn is a number. What is the norm in 1D? Absolute value. Are you all with me, please? So convergence in deterministic world, convergence in probabilistic world. What are the correction, what is the relation between them? Ultimately, every convergence has to talk about the distance. There is a target, I'm getting close to it. How far I am away from the target? What is the distance? If I can squeeze that distance, I'm going to converge to the promised land. But we don't have that freedom here because I'm given only two pieces of information. I got to do with, there is a saying in card game, you have to play the card that is dealt. You can't ask for a card. Is that right? Come on, guys. You have to play with the card that was dealt to you. I want you to think about it. You don't have much of a choice. You are in the game, you have to play with what is given to you. You can't pick the cards you want. Same thing in here. So there's only one story left. I need to compute the variance of this. That's a very simple exercise, but let's do it. So so what is the expected value of x hat? Is equal to a times expected value of x1 plus 1 minus a times expected value of x2. This is equal to x, this is equal to x, that is equal to x. We already know that. All of you? That's right. So the variance of x hat is equal to expected value of x hat minus expected value of x hat whole square. All of you? That's the definition of variance, everybody? That's right. So what is this? This is x hat. Okay, now what is x hat? X hat is a times x1 plus 1 minus a times x2. What is E of x hat? E of x hat is x. So I can write that as a times x plus 1 minus a times x. Add and subtract. All of you? So this essentially tells you I can combine these two, I can combine these two. So this is equal to E of a times x1 minus x plus 1 minus a times x2 minus x whole square. Are you all with me? Come on, guys. This is the x. I wrote this as ax plus 1 minus ax. These two have the same coefficient. These two have the same coefficient. So a times x1 minus x plus 1 minus a times x2 minus x whole square. What's the question? What's that? E of x hat is x. Where did you lose me? E of x hat. So this is, that's E of x hat. With me? E of x hat is x. Are you with me?
Yes.
X can be written as a times x plus 1 minus a times x.
Yes. Sorry.
Aha, say aha, don't say yes. Aha, that's right. Now it looks like a plus b whole square, right? So this is equal to expected value of a times x1 minus x whole square. Expectation of the sum is the sum of the expectations. If you multiply that, I'm going to get 3 terms. Are you all with me? Usual algebra. This is expected value of 1 minus a times x2 minus x whole square plus 2 times expected value of a times x1 minus x times 1 minus a times x2 minus x. Are you with me? You should know your rule from probability theory. What says, how does it say? If the variance of y is equal to sigma square. Variance of A times Y is equal to A square sigma square. If you multiply a random variable by a constant, the variance gets multiplied by the square of the constant. How many of you knew this? That's right. Therefore, what is this term? This term is A square times E of x1 minus x whole square. E of x1 minus x whole square is what? Sigma 1 square. What is this? This is 1 minus A whole square, sigma 2 square. Ah, here comes the problem. It's not a problem, it's a challenge. So what is this? This is the product of these two random variables. The expectation of the product of two differences. That's raised to covariance, right? Everybody? So I'm going to assume my x1 and x2 are independent. So I'm given two pieces of information that are mutually independent. There's no correlation between the two. I did not introduce you at that time. It may look artificial at that time. If it is independent, this term is 0. If it is not independent, there's a correlation between the two. I have to take care of the correlation. I want to walk before I run. So I want to take care of the easy case. So I am being given two pieces of information that are independent. Now, how many of you know the relation between independence and uncorrelation? Independent implies uncorrelated. Uncorrelated doesn't imply independence. In the case where the random variables are Gaussian, uncorrelated is equivalent to independence. So independence is a much stronger assumption. Uncorrelated is a weaker assumption. So do I need independence here? I don't need independence. I only need two uncorrelated information. So independent, uncorrelated. I just want you to be able to discuss this. That's the reason I didn't tell to begin with. Uncorrelated. If it is correlated, what's the problem? They are not giving, there's a common information which doesn't add to the knowledge. Are you with me? If you get an expert opinion, I want two independent expert opinion. Are you with me? That's right. If two people say the same thing, you don't have to worry about them. If two people say different things, then I want to understand. I do believe these two people are good people. Why do they differ? Hey, I want to debate you. I want to understand you. Why is the difference? What is your take on this problem that leads you to have different opinions? All of it me? That's right. But in our friendship, what is that we tend to do? We always try to become friends with those who agree with us. That's a human nature, right? Are you with me? Is it good for your psychic? I'm not going to evaluate. I'm not a psychologist. But oftentimes you need to talk to people who may not agree with you because you learn from them. It's very easy to agree. All of you, I want to bring this discussion because the difference between uncorrelated and correlated. Where uncorrelated comes in, where independent comes in, which is stronger, which is weaker. Uncorrelation is the weakest of the two assumptions. Are you with me? Uncorrelated means what? This product is 0. Why this product is 0? A, 1 minus A. So what is the real value of this term? A times 1 minus A times E of x1 minus x times x2 minus x. I just want this to be 0. So this is correlation. Are you there? So I want that to be 0. That's it. Therefore, without loss of generality, based on my revised assumptions, I'm done with this. So the variance of x hat is this function. Sigma 1 square is known, sigma 2 square is known. Who is the only guy? A. Who picks A? You pick A. But before I go further, I want to give you a geometric interpretation. That's what I came in here. If you have 2 points, there is a line joining 2 points. Sorry, it doesn't look like a line, but it is a line. How do you generate points between the two a times x1 plus 1 minus a times x2. So your point z is said to be on the line segment joining x1 and x2 if z can be expressed a times x1 plus 1 minus a times x2 for all a less than or equal to 1. When a is 0, z is x2. When a is 1, z is x1. As you vary a between 0 and 1, I trace all points from x2 to x1. That's a line segment. Is this a linear combination? It is. So that's a specific name for that. Linear combination, convex combination. Ax1 plus bx2 is a linear combination. When b is 1 minus a and a is in between 0 and 1, that's called a convex combination. Right? So every point on the line segment joining x1 and x2 can be generated as a convex combination of the two endpoints. That's a theorem in geometry. All of you? You all know this, but I just want to bring that. So where does my best estimate lie? Here is x1, here is x2. My best estimate lies somewhere in between the two. We have already seen that yesterday. In the case of 3UR, the optimal estimate lies on the line segment between xb and h of x, z. Now, do you see the same idea keeps cropping up? Now I'm talking about linear estimation. There I was talking about Bayesian estimation. So there are certain fundamental principles kept reoccurring again and again and again. If a basic principle keeps reoccurring again and again and again, what does it mean? It's an important principle. You can't escape that. How many of you with me? Come on, guys. That's right. Oh, good. Now what is left? I need to be able to minimize this as a function of A. Are you all with me now? You have an aha here? That's right. So I satisfied L, then I started with the E, which is L, then I introduced U, now I am working towards B. Each one of them, you work in a different plane. All of it, me? So what is the idea here? Minimize with respect to A such that A in between less than 1, that is a space in which A is going to vary, variance of x hat. This is exactly the way Kalman derived his filter, but with a more sophisticated notation. It's a more sophisticated notation, 1960. 1960. All of you? So the variance is a quadratic function of A. So let's do that now. So partial of variance of x hat divided by delta A is equal to 2A sigma 1 square plus 2 times 1 minus A times minus 1 times sigma 2 square. The differential coefficient is that. Everybody? So this is equal to 2A sigma 1 square plus minus 2 times 1 minus A sigma 2 square. This is equal to 2A sigma 1 square minus 2A plus 2A sigma square minus 2. All of me? Check my arithmetic, please. Make sure I don't screw it up. And I have to equate it to 0. Oh, I made a mistake. I have to multiply this, right? 2 sigma 2 square equals 0. Look at that now. 2A sigma 1 square minus 2 sigma 2 square minus plus 2A sigma 2 square. That must be 0. 2 gets cancelled. I am combining A with A. So this becomes A1 sigma 1 square plus sigma 2 square must be equal to sigma 2 square. That implies A is equal to sigma 2 square divided by sigma 1 square plus sigma 2 square. Therefore, 1 minus A is equal to sigma 1 square divided by with me? Therefore, what is my optimal estimate? My optimal estimate. Can I erase this part, please? So what is my optimal estimate? X hat is equal to ax1 plus 1 minus ax2, which is equal to sigma 2 square by sigma 1 square plus sigma 2 square times x1 plus sigma 1 square, sigma 1 square plus sigma 2 square. Look at that, the sum of the two is 1. That means it's the point in between 0 and 1. Now, I'm going to come to a very important conclusion. So I'm done with the derivation of the blue estimate. But this blue estimate has a very fundamental property. The ultimate aha is yet to come. The ultimate aha is yet to come. So what does variance means? Variance, inverse of the variance in statistics is called information. If variance is large, it can be anywhere. If the variance is small, I have more information, right? Are you with me? It is in between -1 plus 1. It is in between -10 plus 10. The variation is more, the variation is less. If the variation is less, I say the reciprocal of the variance is called information. So there are two things now. If sigma 1 square is greater than sigma 2 square, what does it mean? x2 is more reliable than x1. The variance of x2 is less than the variance of x1. That means I have more confidence in x2 than in x1. So you remember yesterday I talked to you? If you're in a meeting, there is a subject being talked about. If there are a couple of people who are experts in the area, the rest of it will keep our mouths shut. We'll let them speak. Why? We want to learn from the expert. We give more weight to the person who is more knowledgeable in that particular topic. Are you all with me? So here, what is the analogy? You believe, you give more weight to that variable which is more reliable. Are you with me? Let's look at that now. So if sigma 1 square is greater than sigma 2 square, this is larger than that. Everybody, x2 is more reliable. I'm giving more weight. I'm letting the expert talk. All the other guys are keeping a low level. On the other hand, if sigma 1 square is less than sigma 2 square, oh, that's the same, that's a complementary of that. Sigma 2 square is more. Sigma 1 square is less. x1 is more reliable. I'm giving more weight to x1. So that is what's called self-adaptive property. Are you all with me? You always believe, you always give more weight to your more reliable information. You don't throw the less reliable information out of the window, but you diminish the importance. You give more weight to that. I can't simply throw the baby out with the bathwater. You remember? We talked about it last class. Everybody is important. They are in the game. You have to be fair to everybody. You have to respect everybody's opinion. But I may not give the same weight to everybody's opinion because I do know he is more reliable. I do know he is less reliable. Give more weight to more reliable quantity. Are you with me? So that's a natural outcome of that. That's an aha moment. You all have an aha here? Are you with me? Now, I want to do one last thing. I want to So what is this? This is the optimal estimate. Why it is optimal estimate? I plugged in the optimal value of A, buddy. Everybody. A, 1 minus A are two weights. But I'm not talking about any A, I'm talking about the optimal A. Once I replace A by the optimal value, the estimate is not anymore estimate, it's an optimal estimate. Are you all with me? How many of you are with me? Do you all appreciate the adaptive property? Now, what is the last thing I want to calculate? What is the variance of the optimal estimate? Optimal estimate is just random. Why? X1 is random, X2 is random. There are two things. One thing to say the function f attains maximum at x is equal to 0 is other information. What is the optimal value of f at the optimal point? These are two different attributes of optimality. One is called the minimizer. The minimizer is the location. The value of the function at the minimizer. So this is the minimizer. So I'm now going to compute the variance of x hat opt. So what is the variance of this? These two are independent or uncorrelated. So there is no cross term. I have to compute the variance of this product. I have to compute the variance of this product. This is a constant that multiplies that. So the square of this will multiply the variance of that. Therefore, the variance of this is equal to sigma 2 square divided by sigma 1 square plus sigma 2 square whole square sigma 1 square. Are you all with me? Plus sigma 1 square divided by sigma 1 square sigma 2 square whole square sigma 2 square. I'm using the old formulation. If you multiply a random variable by a constant, the variance gets multiplied with the square of the constant. This random variable is multiplied by this, so its variance multiplied by the square of that. Square of that. Now let's look at this now. So what is this? This is sigma 1 square, sigma 2 to the power 4 divided by sigma 1 square, sigma 2 square whole square plus sigma 1 to the power 4, sigma 2 square divided by sigma 1 square plus sigma 2 square whole square. I can take the denominators are the same. I can take the numerator, what's the common? Sigma 1 square, sigma 2 square. So this is equal to sigma 1 square, sigma 2 square divided by sigma 1 square, sigma 2 square whole square plus sigma 2 square plus sigma 1 square. If you cancel this, what do I get? I get sigma 1 square, sigma 2 square divided by sigma 1 square plus sigma 2 square. We are not done. There's one more, aha, yet to come. Sigma 1 square, sigma 2 square, sigma 1 square plus sigma 2 square. I want to ask, is this less than sigma 1 square? What do? You multiply. Sigma 1 square, sigma 2 square is less than sigma 1 to the power 4 plus sigma 1 square, sigma 2 square. These two gets cancelled. Sigma 1 to the power is always positive. Therefore, this is true. Likewise, you can verify this is also true. Therefore, you can say this is minimum of sigma 1 square, sigma 2 square. It is less than sigma 1 square, it is less than sigma 2 square. Is a minimum of less than sigma 1, sigma 2 square. Aha! What does it mean? Sigma 1 square was the variance of x1. Sigma 2 square was the variance of x2. The variance of my x hat is less than the variance of the two quantities that get in. In other words, by doing data assimilation, I have reduced the uncertainty. Is that an aha moment?
Yeah, this is an
If it is not, I don't think I can make you aha at all.
So here we also can say why we do data.
But that, you got it, you got it. This guy has been asking me the question, why do we do data assimilation? Why do we do data assimilation? I've been telling him, wait. This is the moment. So by combining two pieces of information carefully within the context of blue, I can get an estimate. The variance of this estimate is less than the variance of the two quantities that went into creating this estimate. That means data assimilation has helped you to reduce the uncertainty. Is this new to data assimilation? No, it has been known in statistics for a long time. Go back to my coin tossing experiment. Are you with me? We are not trying to do anything new. The problem may be new. The underlying ideas are age old. Let me go back. So P hat is the estimate of P. The variance of P hat resulting from N tosses is PQ by N. Are you with me? I want you to go back and do this problem, please. You've got to do this. You've got to have that aha. Are you with me? So by letting N go to infinity, what do? I reduce the variance to 0. So what does that teach you? By having more observation, if you appropriately design your estimator, you can reduce the variance of the estimate. That means the output is more reliable than the two inputs. Are you all with me? You all have an aha? That is linear minimum variance estimation within the scalar case. Are you with me? So what am I going to do? I'm going to go over to the vector case. I'm going to go to the vector case that Kalman dealt in his 1960 paper. How many of you have heard of Kalman filter? How many of you have seen Kalman's paper? Come on, guys. Is it fair to Kalman? No, it is not. I want you to go back to your home place, download Kalman's original paper, read it. Every time you read it, you get an aha. It's such a beautifully written paper. Are you with me? That's right. You got to go back to the originals all the time in every area. Are you with me? I have seen many people will give Kalman's paper as a reference. They won't even have a copy of the Kalman's paper. Are you with me? That is cheating yourself. So when you write a paper, please don't simply pad the references just to be able to satisfy potential reviewers. You don't refer anything until you have used it. If you want to refer something, you must have at least seen it, touched it, read it, and used it. That's called academic integrity. Are you all with me? Come on, guys. We have to keep our own feet to the fire. So what is the first exercise for you? I have given you several exercises. The coin tossing problem, you have to do the exercise. And he is giving you a whole set of problems. Don't be in a hurry. Remember, 45 years of academic life in front of you. Productive life. Slow and steady win the race. All of you? Any questions? Before I shift to my slides. Why am I going to go slides? These are matrix expressions. They're much more detailed. It will take about 2 hours by itself. Then I have to do Kalman filtering. Derivation of Kalman filtering from basics will probably take another 2 lectures. So having seen this, now I'm going to tell you in what phase Kalman filter uses this. I don't know how many of you know that Kalman filter has 2 phases. How many of you know that there are 2 phases in Kalman filters? How many people raised the hand when I asked you, you know Kalman filter? You have heard of it. You don't know it. Come on, guys. It's not a party talk. You never say I know until you have read it. I have heard of Kalman filtering. I have heard of being used. I don't know it. You want to know it. So what is the crux of Kalman filter? There are two pieces of information, one coming from model forecast. You remember the background information in 3D war. Who gives you background? The background is coming from a forecast from the previous time. And then the new observation comes in. The background is the prior. The new observation is the conditional expectation. You mix it two to get the posterior. That's a Bayesian view. Here, let's say x1 and x2. I said x1 and x2, right? So x1 could be thought of as background. x2 could be thought of as a new observation. I'm trying to combine the two. Now, do you see the same philosophy that was inherent in 3D war in this? Hello? That's right. That's right. Are you with me? How many of you are having ahas now? How many of you feel that things are falling in place conceptually? That's right. That conceptual integrity of thought process is very fundamental. You have to create a picture in your own mind, and all parts of the picture must match. Any questions on this, please? Remember, we fall back on optimization every time. So how many of you know optimization algorithms? Come on, guys. I'm not trying to ask you this question to make you feel bad. Are you with me? Is there anybody who is feeling bad because I'm asking questions like this? You should not. We need to do a self-test. Where am I? Where do I need to go? Are you with me? That's right. So how do you equip yourself to go from here to there? I'm very happy that you are all interested in data assimilation, one of the fundamental tools for data assimilation and optimization. So what is it I would like to suggest to you? Stop doing everything for 2 weeks. Learn about optimization. One second, I want to tell my story. Stop doing everything for some time. Spend 2 weeks, linear algebra, statistics. And keep coming back to these every once in 6 months. All of you with me? And if you did that for a couple of years, nobody can catch you. You'll become expert. It takes time. The best bowlers in cricket, did they become best bowlers? They were born best bowlers? Some of them probably are. They work. The great chefs, they work hard. The wonderful violinists, they work their life out. Are you with me? So being good in anything takes energy, attention. Assimilation is no different. So for your own sake, find out your weak points and try to strengthen your weak points. I'm retired now. But looking back, we have spent a lot of time to get here. Are you with me? And that's what I want to remind you. I thought you had a question. This guy has always a question. Good question.
Can we explain using those expressions why we are not using alone model or observation to predict that?
I have already talked to you about it. Let's say, why do we form committees to make decisions? Have you thought of that? If you have a committee of at least 2 people, if you have a topic, you can get to hear different viewpoints of the same issue. The ultimate decision of a committee is always better than the decision of a single person. Are you with me? A single person, my own idea is good. You are not going to think around. But if you go to a meeting, the other guy says, no, I have a different point of view. Are you with me? So the reason we appoint committees is to be able to get as close to the truth as possible by clever analysis from multiple point of view. That's one thing. Okay? Data, I can't extrapolate data. Now going back to your question, data, I can't extrapolate data. Model is capable of extrapolating, but model by itself has errors. Data has truth. By moving model closer to the truth, I get a surrogate of the truth in the model. Then I can extend the model to make a forecast, which I believe is better. That's the reason. Are you with me, please? That's right. Are you all with me now? Why we do data assimilation? Why we need at least 2 pieces of information? These are all very good questions. Very good. I want you to keep thinking about it. With me? If there are no other questions, let me go to the vector case. Online folks, please, if you have a question, come online.
Yeah. So, Dr. Varahan, I was thinking the way you were explaining about uncorrelated variables, but in most Earth system problems, the variables are correlated, right? Then in those scenarios, how will the variance of output play out
Very good.
under observations being correlated?
Very good. There will be a third term with a rho, the correlation coefficient. Are you with me?
Yes.
Hello?
Yes, I am.
That's right. The third term will also have the product A times 1 minus A. Do you see that?
And with that, yes. And will that be
So
still?
the third term will reduce to 2 times rho times A times 1 minus A.
Okay.
So you have to compute the derivative of that A times 1 minus A. So that will
Okay.
add one more term to the gradient. So the optimal value of A will then depend on not only sigma 1 square, sigma 2 square, but also the correlation coefficient rho.
Okay.
Is it okay or aha?
It's an aha.
Ah, that's right. So you do that with a rho non-zero, you get an expression, then set rho is equal to 0, you will get back this. I didn't do that because I wanted to give that as a homework problem, and you correctly came at the right time to give me another homework problem.
And also, will
Oh,
that
wait,
be
wait,
still?
wait. Is that okay now? Before you go to the next question.
Yes, yes.
Good, wonderful. I'm glad you came online, asked that question. Go to the second question.
So, if that is so, will that still be minimum than the variance of the
Wait a
inputs?
minute. Still be minimum. Once you compute the derivative equate to 0 and check for the second derivative being positive, it has to be a minimum.
Oh, right. Yes, you're right.
May? So there's no
Yeah.
question of if, may, or but. Mathematics gives you a clear guidelines to test when we will have a minimum.
Yes.
Are you with me, sir?
Yes.
Is that an aha again?
Yes. Aha.
Good,
Yeah.
wonderful. Any other follow-up? Anybody else in the online audience have any other question? This is a good question to ask. What is the question? What is the impact of rho if the two variables are correlated? So it's simply an extension of this. There is one more term included, compute the derivative, equate to 0. The optimal value will not only be a function of sigma 1, sigma 2 square, but also a function of rho. That's it. If there are no other questions, we are going to jump to the slides, the vector case. Thank you, sir. Please come online whenever you have a question. Don't be shy. This is the linear. So we have a chapter titled From Gauss to Kalman. That's a historical perspective. Gauss was the earliest, one of the earliest, perhaps the earliest person to pin down the method of least squares. With me? I don't know how many of you know the story. There was a asteroid. Astronomers were observing it. It went out of sight. The problem in astronomy of his time, Gauss's time, Gauss was only a 17-year-old lad at that time. So the astronomers were wondering where it went, when it will come back, it will come back at all. So Gauss, as a young man, took up this project. So he stood on the shoulders of many early pioneers. Kepler had shown that every planet revolves around the mother planet in elliptical orbits. And there were tons of data relating to the position of this object that was lost. So he concluded this object must have been running around its mother planet in elliptical orbits, and I know its positions. Ellipse is a closed curve in a 2D plane. Ellipse is a two-dimensional, ellipse is a second-degree polynomial in two variables, ax squared plus bxy plus y squared plus dx, ey, and f. So there are 6 parameters I need to be able to estimate. So I know it's an ellipse with a known coefficient. I know its positions. So why not I bring the model, elliptical model, with the data together to be able to estimate the parameters of the ellipse? That was the birth of least squares. So once he found the coefficients, then he fell back on Kepler all over again. He used one theorem of Kepler. He went to the other theorem of Kepler. What is the other theorem of Kepler? If you consider a chord, what is a chord? From one of the foci to the perimeter, to the periphery. What is the third or fourth law of Kepler? The chords swept equal areas in equal intervals of time. So he knew the position of the chord when it went out of sight. So he incremented, and he predicted the time it will come out of the shadow. Sure enough, the first experiment in prediction that was successful. To me, that's the birth of data science. To me, that's the birth of data assimilation. So from the data, he built the model. Using the data, he estimated the parameters of the model. Using the basic laws of physics that the model is governed by, he used the model to be able to predict. So the birth of least squares is credited to Gauss. It is in that context, when trying to fit the model to data, he found out that data has lots of errors. He analyzed the properties of distributions of errors. He invented the bell-shaped curve, what we call now as a Gaussian distribution. Please understand, that's the last word. Least squares is used even today. Gaussian distribution is one of the most fundamental distributions in probability theory. Whatever Gauss did was final. I'm going to tell you something that's of generic interest. Gauss was one of the greatest number theorists of all times. There is a theorem in number theory that's called quadratic reciprocity theorem. This man was so enthralled by that theorem, he seemed to have proven the same theorem in 16 different ways during his life. Are you with me? Using 16 different ideas, coming back to the same problem. That goes to show you the depth of his knowledge. So what is the homework for you? Please do Google quadratic reciprocity theorem. You got to know these things. You say, well, I'm not interested in number theory. Please, just to understand the depth of the contributions by Gauss. Is one of the most enduring principles of number theory. Such is the greatness of Gauss. So from Gauss to Kalman. Kalman essentially following the footsteps in statistics applied to dynamical systems. Okay, what is another difference between Fourier and Kalman filters? In Fourier, we want to be able to estimate the initial conditions and parameters. In Kalman filter, I want to estimate the current state. And that's exactly what 3D war is all about. I have a prediction coming from yesterday. I have observation coming from today. I have two truths about today's weather. I want to be able to get to the true state of today's weather by combining the two. And what is the formula that Kalman derived? Linear minimum variance estimate. So he used the model to create the background, the forecast. Then he used the linear minimum variance estimation to be able to combine the forecast with the observation. And this he did sequentially. So Kalman filter is a sequential methods of state estimation within the dynamical context, where the dynamics is not deterministic, but dynamics is supposed to be noisy, and the observations is supposed to be noisy. Linear dynamics, noisy linear dynamics. Linear observation, noisy linear observation. Kalman filter, he wrote the very first paper in 1960. It's a standard today. All of it with me? So I want you to understand fundamentally what is the difference between 4D war and Kalman filter. In the 80s, there was a workshop happened at the University of Oklahoma in 1982-83. Some of the French mathematicians had come and they had developed the 4D war because they were all control theorists. So the 4D war essentially began at the workshop at the University of Oklahoma in the early 80s. Are you all with me, please? Then many of the forecast centers used 4D war. It took 23 years for meteorologists to realize that they can use Kalman filtering in the context of meteorological prediction. In 1983, a couple of people at the University of New York, they did a thesis and found out that Kalman filtering is beautiful theory, but in practice it's impossible to do because the dimensionality problems are too large. Then they went in search of what's called ensemble forecasting, ensemble filtering. That's what my colleague is going to talk about after I finish this. All of it, me, please. So, theoretical ideas, practical implementability, the difficulties of implementation, how to ease the difficulty by working around, how to make the job of prediction more easier, better. So that's a sequence of ideas. So I'm talking about history starting from the early 80s, but Kalman filter started in 1960. Are you with me? Good. There's a theorem in least squares, it's called Gauss-Markov theorem. I didn't talk about that when we talked about least squares. I'm not going to go there. So what does this say? Linear unbiased minimum variance estimate. But I want to get to this is the part dealing with linear minimum variance estimate, similar to the Gauss-Markov theorem, but I'm going to skip this part. Look at that. This is done within the context of Bayesian framework. The mathematics may look a little frightening, but they are very simple. What is the only thing that you do? You simply keep calculating variances and covariances. That's it. Are you with me? Simply put, you keep computing variances and covariances. So that's the algebra you need. Of course, with the context of matrix. Good. So let's come to the Kalman filter static case. What do you mean by static case? I am assuming what happens when I have a prediction and the information, I'm going to combine them together. After this talk, I will talk about the full dynamical aspects of Kalman filter. Are you with me? Good. So let's look at this now. X is the unknown. Here X is a vector, there X is a constant. Let X minus be, X minus means prior. X plus means posterior. With me? So in mathematics, we generally use the symbolism time t, t minus, t plus. What is t minus? It is instances before t. T plus is instance after T. How far? I don't care. This is prior, after. So T minus, X minus. So I'm using X minus, X plus, X at a given time. Are you with me? So this prior information is an unbiased estimate. You remember my x1, the expected value of x1 is x. My x1 was an unbiased information about x. And it has its own covariance. And that, in this case, is a matrix. In my case, it was sigma 1 square. So x minus sigma minus is a prior information. One of the two pieces of information. There, I didn't use the word prior. I simply said one of the two information. I can associate the one of the two to be prior, background. So word prior, background, they are all synonymous. Something you come to the table with. Whenever you go to a meeting, the topic of the meeting is announced. You always think about what should I say there, right? If you didn't say anything in the meeting, then they won't call you for the meeting after some time. Why? This guy doesn't contribute anything. So you have to say something, but it has to be meaningful. All of you? You have to say something relevant in the meeting. So that's a relevant information I have. Then the observation comes in. Observation comes in the form z is equal to hx plus v. V means 0, covariance sigma v. The usual conditions on v. What are the usual conditions on v? X and v are uncorrelated. That means the observation noise does not depend on the unknown to be estimated. Are you with me? Come on guys, that makes sense. That makes sense. So what is the minimum variance approach? I ought to have a x plus, that the linear function of the two pieces of information x minus and z. Here, in my case, it was x1, x2 were constants, so I have a and b. Here, these are vectors, so I'm going to take a matrix L and a matrix K. How many of you heard me? Could I have used a constant? Yes, but I'm losing the flexibility. Are you with me? The matrix has a lot more degrees of freedom. I can control the estimate the way I want. So I'm running parallel to what I did. If you have an aha and scalar, the ahas must be immediate in the vector. Are you all with me? How many of you are with me? So the first part of it is simply a recollection of what I did in the context of 3D war, which I have already done. I don't want to waste your time. Reading that and correlating it is a homework problem. Are you with me? Please. I have been teaching for 50 years. I have never seen a class, if I say homework, oh God, golly, I got a homework. Nobody is happy about homework, right? And you are no exception. But you got to do it. Homework is the bitter pill that gets you out of the disease of not knowing. All of you, please. So what do I want? So I have satisfied L. I have satisfied E. So it's a linear estimate. I want to now make it unbiased. Then I want to make it best. Are you all with me? Am I walking the same path? I have cut a trail. I'm going to walk the same trail, but with a little bit more heavy machinery. So find L and K such that X plus is an unbiased minimum variance estimate. Why do I want you to download Kalman's paper? This is exactly what he does in his paper. Are you with me? That's right. Please understand one thing. Many of you are PhDs, many of you are are working for PhD or planning to work on PhD. Always go to the original source. For every result, you must go to the original source. The best original source for statistics is Dr. Rao's book, the book I told you about. How many of you search for C.R. Rao's book in the Google? Please order a book before you arrive home, it will be ready for you. It's a Bible. With me? So L and K, find L and K such that X plus is an unbiased minimum variance estimate. So once I have the framework, so what is rest? Is simply busy calculations. Everybody? So concept is done. I simply need to be able to implement that concept. That involves some tricky calculations, algebra. If there is anything you should not be afraid of, is algebra. Are you with me? If anything that you should not be afraid of is algebra. So I want to introduce unbiasedness. This is x plus. I want the expected value x plus to be x. That's a condition for unbiasedness. X plus has this structure. Z is equal to hx plus v. I substitute, simplify. Expectation of the sum is the sum of the expectations. Expectation of v is 0. So L of x plus kh L of x. So x must be equal to L plus kh x. That essentially tells you L plus kh must be equal to I. Do you remember A plus B must be equal to 1? How many of you with me? Nothing could be more beautiful than this. Nothing could be more beautiful than this. Why did I not have a h there? My x2 itself was an observation. Now I want to tell you when do you need a h and when you don't need a h. Let me talk about that for a moment now. I know I may spill over to the next week, but these are important things. Pressure I can measure directly. Temperature I can measure directly. Vorticity, can you measure directly? No. So observation, some physical quantities are directly observable. Many physical quantities are only indirectly observable. Are you with me? They are called derived quantities. So H, in some sense, represents that relating the state to the observation. So in the case of temperature, H is identity. In the case of pressure, H is identity. In the case of velocities, I can measure them. If I'm going to measure temperature from radiation, then I need a H. If I want to measure the amount of rain through radar reflectivity, then I need a H. So when you need a H, when you don't need a H, when is H is linear, when H is non-linear, that depends on the kind of observation you plan to use for your problem. Are you all with me? There in my case, I didn't say Z, I had X. That means I'm assuming my observations or state themselves, I'm directly measurable. Everybody? That's the simplest possible case. That's right. Therefore, that condition essentially leads to L must be equal to I minus KH, B is equal to 1 minus A. Substitute this is the structure of that. So this structure is beautiful. This is the structure Kalman that underlies the Kalman filter. What does it say? The posterior is equal to prior and a correction. The correction depends on Z minus H. So Hx minus, what is that? That's a model predicted observation. Z is the actual observation. The difference between the two is called innovation, new information. That's called innovation. I know what I know. I want to know what I don't know. That's why you talk to people, right? Hey, that's the reason I always tell you, if you are in a friend circle who all agree, you never learn. Each of you fooling each other. I want to know what I don't know. So Z tells me something, H of X minus A says something, the difference is something I did not know to start with. So what am I trying to do? I'm trying to add a multiple of that innovation to this to get the new estimate. And what is K? K is called the Kalman gain. K is a matrix. Now, what is X? X is a n vector. Z, H of X, these are m vectors. So Kalman gain is a rectangular matrix of size n by m. So what is the whole question? What is the optimal value of K? You remember that, what I did? What is the optimal value of A? My A plays the role of K. A was a scalar, H is a matrix. Now what is that I now need to do? I need to be able to compute the total variance of X plus. Total variance of X plus. X plus is a vector. X plus has a covariance matrix which is n by n matrix. How do you define the total variance of the vector? It is the sum of the variance of the individual components. And what is that? It is the sum of the diagonal elements of the covariance matrix. And what is that? That is the trace of the diagonal matrix. So what is that I want to do? I want to be able to minimize, I want to find a K such that the trace of the covariance of X plus is the minimum. How many of you are with me? How many of you wanted to learn Kalman filter? Are you learning? How many of you are learning? Come on, guys. Good.
Here,
Yeah.
in the last step,
Ah.
our X prior is n vector.
Yeah. H is m by n.
H is m by n.
That's right.
So then X.
He's a careful guy. That's right. Innovation is a m vector. I need to convert the m vector to a n vector. I have to multiply by a gain k. K must be a rectangular matrix of size n by n. So what is the mathematical problem? Find k that minimizes the trace of the covariance of X plus. Now you know why I didn't do this problem first. If I did this problem, you will hate me for life. Now I have given you a handle how to do that, so you can walk that path. So what is the rest of the story? The rest of the story is to be able to do that. I'm going to leave it as a homework problem, or maybe I can talk about it for a few minutes after the tea. The tea is hot, waiting on us. Let's take a break. We'll come back at
11:30.
11:30. Thank you.